In alkene, you have got at least one CC double bond. This is ethene, and here we have got a double bond. Double bond means that we have sp2 hybridization here and here. Double bond is a short bond. If you compare C double bond C to C single bond C, then C double bond C will be a short bond. So in alkenes you have C single bond C. That will be a longer bond than C double bond C. sp2 hybridization means 120-degree angle, but that is only approximate. It can be accurate also if all sides we have got similarities. Here, all sides we haven't got similarity. Hydrogen, hydrogen, carbon. So the three bonds are not 100% same. So little deviation from 120, and that you can see here, 117, 121. In case of ethene, both carbons are sp2 hybridized, and there is no other carbon. Both are sp2 hybridized means geometry is planar about both of them. That means the molecule is going to be completely planar. Otherwise, in case of alkene, it is possible that molecule is not completely planar. Some part of it may be planar and some part of it may be three-dimensional. But in ethene, there is no carbon which is sp3 hybridized. If you have sp3 hybridized carbon present, then it won't be planar everywhere. Say for example, you have got propene, right? In case of propene, two carbons are sp2 hybridized and third carbon is sp3 hybridized. So for sp3 hybridized carbon, the geometry is three-dimensional. So the whole molecule is not planar. Likewise, if you go to butene, one butene let's say, or you go to one pentene, if you look at one pentene, most part of it will be non-planar. In one pentene, two carbons are sp2, two carbons out of 5, and other 3 carbons are sp3. So all of those 3 carbons are non-planar, three-dimensional, and 2 carbons are planar, two-dimensional. So calling pentene, one pentene, as a planar molecule is wrong. So alkenes are planar. Well, that statement is not 100% correct in all situations, but you have to understand what could it imply. It could imply that those locations which have got double bonds, those locations are planar. The whole molecule need not be planar, right? But ethene is planar. So we talked about double bond. Now double bond means that there is one sigma and there is one pi. sp2, sp2. sp2 means three orbitals. sp2, each orbital is called sp2. So sp2, sp2, sp2. There are three orbitals. But there are three p's, and in sp2, two p's are involved. So one p is alone. One p is alone. If we talk about p subshell, then it can be thought of as three mutually perpendicular orbitals, px, py, and pz. So s and two p's out of three p's sort of merge, and if s, px, and py sort of merge, s, px, and py, if these three merge, then you get three new orbitals. Each one of them is called sp2, and these three sp2 orbitals lie in a plane. Can you tell me which plane that would be if px and py are involved, pz is not involved in hybridization?
Sir, XY plane.
XY plane. So these three lie in XY plane, and that fellow which is not participating in hybridization, which is pz, that fellow will be perpendicular to this XY plane. So both carbon atoms you have to visualize like that. pz, pz. So these three orbitals sp2, each has got 1, 1, 1 electron. pz also has got 1 electron. So 4 electrons that carbon has, I'm talking of outermost shell, 4 electrons. These 4 electrons live in sp2, 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 and 1p, which is perpendicular to the plane containing sp2 orbitals. That pz is of great importance to us because that pz is not able to bond that well. It is not able to bond that well. See the difference. Now imagine some sp2, say this finger is sp2, one of sp2s, this finger also sp2. So they overlap somewhat like that, right? That's a nice overlapping. Nice overlapping denotes strong bond. Strong bond is a happy bond. On the other hand, in case of pz, perpendicular, if this plane is xy plane, the plane where three sp2 orbitals are living, then the perpendicular is pz. So left carbon atom also has this plane, right carbon atom also has this plane, right? Then both of them have got perpendiculars pz and pz. Now these pz cannot overlap like that. They overlap like that, from top also and from bottom also. So they can't overlap like that. So they have no choice but to overlap like that. This is not a great type of overlap. It's a weak bond. It's a weak bond. That makes alkenes very interesting because weak bond means reactive. Weak bond means reactive. So overall it may look like it is so that CC bond length is less because it is C double bond C. If you compare that bond length with CC bond of alkane, then you will find that this bond length is less because it is sigma plus pi. But sigma plus pi is not equal to 2 sigma. Sigma plus pi is less than 2 sigma. So the second bond is weak and because of that we would expect greater reactivity. And one more thing, not just pi is weak, it is like two balls, and in their region, in a common region between them, not only between them because electrons circulate also, let's say surrounding them, surrounding these two balls, in that region there are four electrons. In one sigma bond, 2, and in one pi bond, 2. So 2 plus 2 equal to 4 electrons are there. And if in a region there is greater electron density, then an electrophile would be interested. So some species that is looking for electron density, that species would be interested in attacking this region. And because this pi bond is somewhat not excellent overlap, it has still got some hunger. I already said that reactivity point will be there more in case of pi bond. Because it is not an excellent overlap, there is some hunger for bonding, better bonding. So pi bonding, something better than pi bonding, there will be a hunger for that type of thing. So alkenes you would find much more reactive. There is much greater chemistry associated with alkenes. So we get to think of these things when we look at the bonding and the structure. We can imagine what types of chemical reactions are yet to come. Conversion of pi bond to sigma bond by addition reaction. We can foresee that type of thing coming right now. So that's what you are seeing here, the sideways overlap, not great. All right. But as far as polar character is concerned, well, that's not going to be much significant, polar character, because after all, we are dealing with carbon and hydrogen. So that means dissolving in water, those types of things, we don't expect anything vastly different from alkanes. When we look at intermolecular forces, we don't really expect something vastly different happening in comparison to alkanes, right? Similar hydrocarbon type of network we have got here. Isomerism, you have seen already isomerism in alkene when we discussed nomenclature, cis-trans isomerism. So we can talk of difference in structure itself, difference in structure when we say it's like one butene, two butene type of thing. Structure itself is different, location of double bond itself is different. But it is also possible that structure-wise there is no difference, but still there is difference. Structure-wise there is no difference, but there still is difference in space. So that gives rise to stereo isomerism. And we talk of cis-trans isomerism in that context. So we have structural or constitutional isomerism, and we have got stereo isomerism. Let me quickly show these points via an example. Look at this species, carbon 4 species. 1-butene look at this is 2-butene. This is also 2-butene. 2-butene versus 2-butene. So 2-butene and 2-butene, that means they've got the same structure. They've got the same structure. They're not structural isomers. They are not structural isomers. But CH3 on one side of the double bond, CH3 on the opposite side of the double bond. Geometrically, you will find difference. Space, location, different. So these two are going to be stereoisomers. This is 1-butene, this is 2-butene. Double bond has got a different location. These two are going to be structural or constitutional isomers. 1-butene, 2-butene. Double bond has got different locations. These two are structural or constitutional isomers. And this fellow looks completely different from either left or any of the bottom fellows. So it is constitutionally or structurally different from this also, this also, this also. So these two are going to be constitutional isomers. These two are constitutional isomers. These two are constitutional isomers. So look at these three. 1-butene. If numbering itself changes, if nomenclature itself changes, not cis-trans, the primary nomenclature changes without cis-trans, then they have got to be constitutional isomers in case of alkenes. But if it is just the difference between cis and trans, then they have got to be stereoisomers. Here in this, you find that even primary way of nomenclature has changed, not just cis-trans, constitutional isomers. But if it is just a difference between cis and trans, whereas the major part remaining the same, then it is constitutionally the same thing. Only spatial arrangements are different. CH3 on one side, CH3 on the other side of the double bond. Does it really matter? Well, if it did not matter, we would not have learned it in this way. It does matter. So there is difference in this and that. And you will see that in this topic to some extent. What's the difference in this and that? In nomenclature, we have discussed in detail cis-trans idea, their meanings, etc. Now, this point I have mentioned to you earlier. And when we were discussing conformation, I think that time I probably mentioned it. It's like a vertical glue. So vertical glue means you can't rotate. This axis rotation. In case of alkanes, yes, possible. But imagine a glue at the top and at the bottom. Now, how do you rotate about this axis? There's a glue at the top, there's a glue at the bottom. That glue was not there in case of alkanes. So rotation was possible. And that's how we talked about so many degrees rotation can take place, and two special cases out of so many degrees. Right? But here's how to rotate. Top, bottom, glue. So that type of rotation is not going to work here. So cis to trans conversion, not easy. If you want to make it work, then a lot of energy will be required so that you are forcefully able to twist. You are forcefully able to twist. It is not willing, but forcefully you are able to twist. And you somewhat like breaking the glue at the top and the bottom by trying to twist. So twisting and bringing this ball here by rotating this axis requires energy, not easy. That's not so difficult in case of alkenes. Yes, we discussed that energetically there could be a more favorable form. There could be a more favorable form rotation-wise, conformation-wise. But that energy gap here is going to be very big. Their energy gap is not going to be so big when we talk about conformations. Here energy gap will be big. So this fellow turned here and brought here, energy gap is going to be much larger in the process of rotation. So that is the energy gap we are talking about. So if you want to go to this state, from this state, well, finally it may look like energetically more favorable. Look at the lower potential energy in comparison to this. So finally it may look like a happy situation. Finally. But there is a barrier. There is a barrier. So there is water here. Water wants to go down. But there is a hill. So water always wants to go down. But there is a hill. So unless it climbs that hill, it can't go down. So that energy barrier is there, and that is there because of this this gluing effect at the top and the bottom. So once you prepare alkene in certain form in your lab, there are methods of preparation giving you different types of alkenes. So if you have prepared cis alkene, or if you have prepared trans alkene, then that conversion from one to the other is not going to be that easy. It's not going to be that easy as it is in conformations of alkenes. Carbon and hydrogen, almost similar in electronegativity. So you don't really expect much polarity to exist. But there can be unsymmetric situation, and that may give rise to slight dipole moment. That means slight polarity. We talked about the stability of free radicals in alkenes. In that you saw how alkyl group would stabilize free radical. So if experiment tells you that for this alkene, dipole moment is 0.3 divine, And you are wondering if the dipole moment vector would be downwards or upwards. You see why I'm talking about this part, because for this it is 0. So if this has got non-zero, it must be due to this CH3. Right? Now the question is, should CH3 be releasing? Releasing electrons means will it be positive, sending the electron cloud towards this side, or should it be pulling electron cloud towards its side and it becoming minus? Dipole moment is a vector quantity, right? So in which direction we have got dipole moment vectors? It is just like answering this question, that which is positive, or it is same as answering this question, is CH3 releasing electrons or it is withdrawing electrons? You have some idea about stability of free radicals, so I think you can answer this question making use of that. But let us do it in a different way, and then we can merge this discussion to free radical stability discussion. Right now let's do it in a different way. We have to answer this question, if CH3 is releasing electrons to the double bond or is withdrawing electrons from the double bond. Okay? So how do we answer this question in a different way? We look at other experimental results. We look into this alkene, which is substituted alkene. Chlorine has taken the place of hydrogen. And in this we find it is 1.4 debye. That's expected. Carbon and chlorine, large electronegativity difference. So it has got to be polar. And we also know the direction for sure. We know chlorine is more electronegative. So plus has to be this, minus has to be that. Plus to minus. Or whatever convention we are following. So it is pointed from plus to minus here. Now, we have got experimental result for this also, which is 0.3. 0.3 for this, 1.4 for that. If we look at this molecule, experimental result gives us 1.7. What does it mean? 1.4 plus 0.3. That means the two vectors should be supporting each other. Only then can they add. So what do you think? Which is plus? This is plus or this is plus?
3 is plus.
This is plus or this is plus?
3 is plus.
If C is plus, then how will the two vectors add? Okay, both are C's. So which C is plus? CH3 C is plus or double bond C is plus?
The CH3s.
CH3.
CH3 C is plus. Yes. So when two vectors are parallel, then they add. Now it is perfect. Plus to minus, plus to minus. Two vectors, same direction when they have got and they are parallel, then they add. So this tells us that CH3 releases electron towards this site. That also tells us that double bond of alkene must be electron hungry a little bit. Double bond of alkene should be electron hungry. That is also understandable because that pi bond is a partial bond type of thing, or not like sigma bond, let's say, if not partial, not like sigma bond. Overlapping is not excellent. Carbon bonds 8, both sides, 8, 8. 7, 7 are there. So 7, 7 were there, then they decided to overlap and they went for pi bond. Pi bond worked, but not that well. So some hunger for electron is still there because the overlapping is not excellent. So both of these carbons become somewhat demanding. I want electron type of thing. So this methyl is present here, and you can imagine what effects must be taking place. You have seen how methyl group releases electron to a free radical case via hyperconjugation and a little bit of sigma release also. So that shows two things, that something like methyl can release electrons, and it also shows that there is some hunger for electron in this region, probably due to the partial or not sigma type of overlap that takes place between perpendicular P and P. Lateral overlap is not as good as axial overlap. So probably due to that there is some hunger for electron. So that demand for electron is there, and methyl is providing it to some extent. So that slight deformation of electron cloud towards this site gives it somewhat positive character. So you have got a little dipole existing here, little, just 0.3 dB. Now we have got a very nice synergy working for us. Free radical chemistry and this chemistry, double bond, and also carbocation chemistry. They all are sort of meeting, and they all have got a common explanation. Free radical, alkene double bond, and carbocation, these three things. They all seem to be hungry. Free radical is understandably hungry. Carbocation understandably hungry. In double bond, it may look like 8 electrons are fulfilled. 8 here also, here also. So why? So the answer to why lies probably in that lateral overlap, making it also somewhat hungry. So two vectors, plus minus, adding, plus minus, to give this. Yes, this is what I was talking about actually. The three things are getting connected. In free radicals, we find this, that this is more stable than that. In carbocations, we also find this. Same story. This is more stable than that. And by the way, carbocations are even more hungry. How many electrons do you think are there with this carbon after these bonds? After these bonds, how many electrons are there? It's positive.
And
Can you repeat?
So 0.
Sir, 5.
It is just single plus, and without, I'm talking about outermost shell, okay, just outermost shell. So it has got 4 generally speaking. It has got plus charge, and then it has got 3 bonds. So including those 3 bonds, how many does it have now? Outermost only.
So 6.
6. So it had got 4. 1 is gone, 3. So it has got 3 of its own. It finds 3 partners. So including those 3, 6. So this carbon must be really hungry for, desperate for electrons. This fellow has got 7. It is hungry. So Alkyl makes it happier because this species is more stable than this. So we can say it does make it happy. And here also we have got the same story. And now we have got one more story, which is double bond. Here it is. We are arriving at a very important conclusion that alkenes that are more substituted alkenes should be more happy alkenes. Alkene would rather like to have alkyls than hydrogens, where double bond is there, connected to the carbons between which double bond is there. If alkyls are connected to those carbons, then alkene will be more happy than the situation when hydrogens are connected to those carbons. That's a very important result. So often you will face that situation of mixture. This is also getting formed, that is also getting formed, that is also getting formed. And you have to decide which one should be major, which one should be minor. So the stability aspect, nature, what does nature prefer? Generally speaking, stability. So then you have a clue that this alkene is more stable, so I should form that in majority at least. Less stable should be in minority. More stable should be in majority. And you will find this type of logic will work in most cases. There will be some exceptions where some extra factors will come in. Say for example, a more stable thing wants to form. A more stable thing wants to form. I think that diagram, yes, it is there. Sometimes it happens in nature that more stable thing wants to form, but some problem comes in. Yes. So there may be cases where more stable thing cannot be formed because some other problem has come on the way. But generally you will find that this logic will work very nicely. You have to decide which alkene should I show as the major alkene. So then you know I should go for more substituted alkene as a general rule. And barring a few cases where something else is not letting it happen, some barrier sort of a thing is not letting it happen. So crowding is one thing, in which case most stable alkene is not formed. Crowding is one case. Somebody wants to reach some point and there's a lot of crowding in that region, is not able to reach there. So it is not able to form some particular thing due to that. So those situations do take place sometimes. So now you have a general rule regarding more stable alkene. The more substituted alkene is more stable alkene. Theory should always be backed by experimental facts if possible. Sometimes it takes years to verify the theory experimentally. In case of alkenes, how do we tell about the stabilities experimentally? In case of alkanes, we must have talked about combustion. In alkanes discussion, we must have talked about combustion as a tool to judge the relative stability. Can we do something like that here also? Alkene, after all, is hydrocarbon. So why not go for combustion reaction and measure the heat of combustion? If alkene is more unstable, it should be giving more energy. And if alkene is more stable, then it should be resistant to reaction. If something is happy on its own, why would it react? Inert gases are rather happy on their own. They don't like to react. So if alkene is stable on its own, comparatively, then it could be less willing to react, giving less energy. Alright, we are reaching towards that point, that how do we do it experimentally? Stability comparison. I was saying that as a general rule, if more alkyls are connected to these two carbons, the better it is for stability. Only one alkyl here, mono-substituted. Two alkyls here, di-substituted. Two alkyls here. These two cases may be interesting cases. Which one to go for? This is also di-substituted. And even this one, di-substituted. Then 3, tri, and this should be the best as far as stability goes. All tetra substituted. Now, as a general rule, I said that more substitution should mean more stability. That's pretty obvious, that di-substituted should be more stable than mono-substituted. Now, here comes another point. How about cis and trans? How about cis and trans? Suppose I have got R, 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 R. Both are di-substituted. Now how do I compare which di-substituted is more stable? Again, Coulomb's law will help us. Organic chemistry is all about electrical forces. We find that, theoretically, we find that if things are close, if electron clouds are close, there should be larger repulsion. And if electron clouds are farther, there should be smaller repulsion. And experiment supports us, so we have got a theory that works. Trans has got electron cloud at larger distance, less repulsion, more stability. Cis, electron cloud close, larger repulsion, less stability. So if you are to compare cis versus trans, go for trans. This is what I was saying earlier, experimental verification, and not just verification. Sometimes experiment leads to theory. Sometimes, many times, experiment leads to theory. Sometimes it is verification of theory. Sometimes it gives rise to theory. So if you look at C4H8, then various C4H8 are in front of you. Here you find that there are two hydrogens. One hydrogen is here. So this fellow is mono-substituted. Here you find one hydrogen, di-substituted, two alkyls. Here you find one hydrogen, di-substituted. Here you find two hydrogens, but both hydrogens are substituted. So di-substituted, mono-substituted. So no doubt, theoretically speaking, that should be least stable. And experimentally we find that it does give most energy. Most energy means it is most desperate to react. It should be less stable. It should be least stable. Here he also says the same thing. Very good. Now we have got a little problem. All of these three are di-substituted. We do have got something to say regarding cis versus trans. That we can handle theoretically. So theoretically we know that trans should be more stable. What does experiment say? It says 2710 against 2707. So trans is giving less energy. So it supports the theory that less energy it gives, it should be more stable. And we also say the same thing theoretically. That theory works well. The only thing left now is this. And I think for that, one can just look at the experimental number. That's it. One can just look at experimental number for that thing. So we don't really have a great amount of explanation for that. So this is giving 2700, 7 less. So that means if it is the same carbon, which is getting substituted, rather than different carbons that are getting substituted, then the same carbon substitution is appears to be more favorable to stability than substitution from different carbons. That we can say by looking at experimental number. Any questions? Let me know. Now here is a problem for you to try out. C6H12. There can be so many C6H12. Which one do you think would be most stable? You can use the board if you want. You can do some hit and trial. In fact, that itself is the answer. If you put C, 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 that itself is the answer. So if you put C, 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 C everywhere, it means it is ultimate, all substituted. That's the maximum one can do. So that should be the most stable out of all C6H12 structures. CH3, 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 CH3. That's it. Fine. We stop now.